Hello everyone and welcome. My name is Bob Hansen. I'm with GE Industrial Systems and I am a specification engineer located in Overland Park, Kansas. Thank you for joining today's session. Today I'll be talking about modeling arc energy reduction in the EasyPower software, specifically covering a couple of the options that are cited in the Article 240.87 of the 2014 NEC. I will be monitoring questions in the questions option of your webinar interface, so you can feel free to enter those at any time, depending on where I'm in the presentation. I may answer them as we go along, but certainly I'll get to them at the end if we don't get to them as we're going through the presentation. I'm required to show this disclaimer by my company's rules. Bottom line there in the bottom paragraph is if you continue to listen and attend this webinar, you're agreeing that any use of this information by yourself that results in some sort of loss, you would hold GE harmless in that situation. So the plan of attack agenda for today is as follows. We're going to do a quick review of Article 240.87. We're then going to talk about some basics of maintenance switching and then talk about how to model it inside of EasyPower. Then we'll do essentially the same thing for zone selective interlocking, talk about what it is, and then talk about, again, how to model it. The modeling results that I am showing are based on the EasyPower 9.8.1 version. I'll also point out that some of the specifics of choosing settings and various options you'll see will be based on the GE breakers trip units that I am using. Since I'm a GE employee, those are the breakers I know best. And that if you look at any other vendor's implementation of ZSI, there will be some differences. But overall, the key principles I'm talking about today in terms of setting key pickups below the arcing current values would apply to anybody's technology. Okay, so here's the first part of the statement of the 240.87 article based on the 2014 code. I'm displaying this similar to how you'd see it in a handbook where the changes from the previous edition of the code are highlighted in yellow, although we're not going to talk about those changes. But the bottom line is the statement says if you've got a circuit breaker that can be adjusted to 1200 amps or higher, then you must comply with the two parts of this article. The first part's pretty simple. You have to document where those breakers are located. And to this point, we can say that this is going to apply based on the code's definition of low voltage to systems 1,000 volts or less. And it doesn't matter what type of breaker we're talking about as long as we're talking about low voltage. It could be a molded case circuit breaker, so certainly 1,200 amps, 1,200 amp molded case circuit breakers exist. It could be an insulated case circuit breaker, or it could be a low voltage power circuit breaker. This would apply to any of those as long as you meet the opening requirement for 1,200 amps or higher. So on to section B of this article. Here are different options. The code says you must choose one. You could in fact have more than one, but obviously the minimum is one, to reduce clearing time. Now the code doesn't specifically say what clearing time they're talking about, but as you'll see, it is talking about the time it takes the method or device to clear an arcing fault, because that's the time that matters when we're talking about the resulting arc flash incident energy. So within this list, the first one is zone selective interlocking. This is typically a trip unit based function that will interlock the responses of the short time parts of the protection or the instantaneous parts or both. The other item we're going to focus on today is going to be the energy reducing maintenance switch. And again, that is typically an option that exists on the trip unit. Again, for low voltage power circuit breakers, insulated case circuit breakers, and molded case circuit breakers would typically, at least the larger size molded case circuit breakers would have this feature available. Certainly the other options listed here are noteworthy and deserve their own discussion, but again for today we're going to focus on these two methods to discuss how to model them inside of EasyPower. Also, Some of you may be aware that there are changes in the 2017 that add a couple of other options to this list. We can certainly discuss those in the questions and answers part of the presentation. But basically, again, the principles of setting the key pickup you're using below the arcing current would apply even with those changes in 2017. But since last time I checked the NEMA map, only one state was following 2017 thus far. 2014 is still very relevant. Okay, if you've never seen a maintenance switch before we get into any details, just to give you an idea. Again, the term maintenance switching, maintenance mode, I tend to use those interchangeably. In many cases, but not 100% of the cases, there is a physical switch involved. And the two photos on the left are a picture of a group-mounted switchboard section. And again, the way GE would do it, we would put all the associated maintenance switches, the physical switch, on a panel at the top of the switchboard, and then the lower picture you see on the bottom right shows the sealable covers that are associated with each circuit in the feeder section that would have the maintenance switch function. If you have an individually mounted device, such as in the top right picture, where we're showing a low voltage power circuit breaker with a typical cassette underneath that. Again, the way we do it, the maintenance switch is mounted in that cassette, again with the sealable cover. As I mentioned, you don't necessarily have to have the physical switch. So in the case of, say, our GE Intelligent switchgear, it's all software controlled, so it's either point and click on the laptop, or if you're in front of the HMI screen, you're touching with your finger to put an individual breaker or every breaker in the system into the maintenance mode. All right, so before we talk about modeling this capability, let's talk about some of the basics involved here. First good thing to understand is when we say a maintenance setting, it's basically a second instantaneous setting that is available on the trip unit. The setting would typically, and actually should be, different than your normal instantaneous setting to get the effect of an arc energy reduction. The setting that you would have to set it to should be determined by a system or arc flash study. The mode, the maintenance switching function, can be enabled, that is turned on and off, via the local switch I showed you examples of, via HMI, if that is part of the system, or a remote switch, or via communications if the trip unit is also a communicating trip unit. The maintenance function is intended for temporary activation only when a worker is going to do something inside the arc flash boundary. The reason that it's considered as a temporary measure only is because as you choose lower and lower maintenance settings, you're going to create more overlap with downstream devices, and that overlap would not be coordinated. So if you look at the couple of panels on the right, the little graphics, these are examples of what, say, a GE trip unit would look like. You'd scroll through the interface of the trip unit, through long time, short time, and eventually get to your instantaneous setting. And there you're entering in a pickup here showing a 10x multiplier, typically of the rating plug value, so 10x times rating plug. And if you were to continue to scroll through those settings windows in, again, a trip unit optioned with the maintenance switch functionality, you get to another window indicating that's what it is. So for GE's implementation, our name for a maintenance switch is called RELT. That stands for Reduced Energy Let-Through. So if you see that on some of the example graphics I'm using, that's what it stands for, Reduced Energy Let-Through, but it is the maintenance switch. So that is what the bottom graphic is showing you. This is the instantaneous setting that's associated with your maintenance option. And here you see the pickup is at a 1.5. So while I said the maintenance switch setting is like a second instantaneous, it's not exactly in every respect like an instantaneous setting, because your normal instantaneous on a GE trip unit goes down to typically as low as a 2.0 multiplier, but our maintenance setting typically goes down to as low as a 1.5. So there are some minor differences like that. Some other basics that are very good to understand when analyzing what's going on with the maintenance switch. One of these points is that it's good to understand the maintenance switch really can't differentiate between what the fault is, what type of fault it is, whether it's a bolted short circuit fault or whether it's an arcing fault. All the trip unit is using is its normal CTs and the algorithm in the trip unit. There's really no other technology that's going to allow it, associated with a maintenance switch, that's going to allow it to differentiate the type of fault. It also can't differentiate what the location of the fault is. So, of course, if you have a fault above where the maintenance switch is located, the maintenance switch is irrelevant. But if the fault is on the bus immediately above where the maintenance switch is, or buses below, again, the maintenance switch cannot differentiate. It only knows it has a pickup, and again, the other associated algorithms in the trip unit. It should not influence the arc flash label in the sense that a temporary measure should not influence the arc flash label. Typically, what should the incident energy reflected on the label should be the worst case condition for all the operating modes of that particular lineup. As I already pointed out, the setting range on the maintenance instantaneous can be different, and it is different than the normal instantaneous range on a GE trip unit. And again, the maintenance setting should be set below the arcing current range that's calculated in the software in order to get the full effect of the maintenance mode. So we're going to show some examples of setting windows and time current curves, but to kind of give a little perspective to this first, this can be considered the one line. I've got a 50 kA source. Feeding, we can consider this a switchboard bus, but all the principles I'm going to talk about would be the same if this were switch gear. So I've got a 2500 amp main and some variety of feeders. For the time current curves I'm going to show, we're going to have a 2500 amp main time current curve, also shown with the largest feeder. So you can see not only the arc flash implications, but also the close cousin selective coordination implications of what we're doing. So here is going to be the baseline setting of the main breaker shown in cyan, and the downstream 1600 amp breaker shown in purple. Obviously, there could be different ways to set these up as a baseline, but I think this is a fair baseline setting that also will allow you to see, as we progressively try the two technologies we're going to work with, you can see exactly what's happening in the time current curves. The other thing I want to point out is that we're focusing on the main breaker for these examples. In other words, we're going to try to meet the code requirement using either maintenance switching or ZSI for the 2500 amp breaker. When we get into the maintenance switching modeling, it's pretty simple because we'll only be working with the windows associated with the 2500 amp breaker. Once we get to ZSI, we'll be working with windows of the 2500 amp breaker and the 1600 amp breaker. And you might then get the impression, oh, I'm also meeting the code requirement for the 1600 amp breaker because it's above 1200 amps too. We have to meet the code for it. That somehow doing a ZSI connection between those two breakers also meets the requirement for the 1600 amp. That's not the case. So again, I just want to point out everything we're doing is with focus on meeting the requirement for the 2500 amp breaker. For the 1600 amp breaker, you'd have to make an independent decision there as to what it needs to meet the code and what's best for the situation. So independently, you might put a maintenance switch on the 1600 amp breaker, or you might join it in the ZSI scheme with something further down in the one line that we're not showing. And as I mentioned, I will be showing some of the arc flash results that are reported by EasyPower. And this will all be based, for everything I'm showing, all based on the same set of conditions. A 32 millimeter gap, an 18-inch working distance, and again, a 480 volt solidly grounded system. Okay. So on the left-hand side of the slide we're now looking at, we're seeing, again, the baseline setting. And the first thing I want to point out is there is one part of this graphic that is added in PowerPoint, not part of what EasyPower does, and that's the dashed line, vertical dashed line I'm showing, where arrows going to the right, that shows a non-coordinated region, and arrow going to the left showing the coordinated. So what I'm indicating there is up to that point, and that dashed line represents where the instantaneous parts of the curve start to overlap. If you look to the left of that dashed line, I can see white space everywhere between those two breakers, and that visually tells me they're coordinated. But to the right of the dashed line, I have overlap in the instantaneous region, and we're going to be able to deal with that and get that coordinated once we get to the I-ZSI part of this, the instantaneous zone selective interlocking. But for now, For large breakers this size, it would be expected those are not, that area is not going to be coordinated where they. Everything else you see on the screen is from EasyPower, again, within the time current curve view. The other thing, hopefully you're aware of, and in using the arcing current flag that's available, this little red flag that's labeled, in this case, 100% arcing current, 24,000 amps, is obtained by right-clicking on the upstream breaker and saying display the arcing current flag. The detail graphic on the right, again, is basically just the lift of the instantaneous and short time region to get a little more of a close-up. And I've also added this rose or reddish colored band. Again, that's done in PowerPoint, not in EasyPower, to give you a stronger visualization that there is a range of arcing current that we're working with and have to consider, not just a single value. And this is per the IEEE 1584 standard and is inside of EasyPower, but EasyPower is displaying the arcing current value that, the arcing current percentage, 100% or 85%, that drives the higher incident energy. So basically the way to look at this is, if I look at the rose-colored band and trace it up to the main breaker, there are really two key points there. There's the point where that band intersects the time current curve at the little area I'm highlighting now. And because the range of arcing current is cleared at the same time, whether you're on the low side or the high side, the higher arcing current value at this clearing time produces the higher incident energy result, 9.4 calories per centimeter squared in this case. Then that's the point, the 100% value that drives it. So in this case, the 85% point does not produce the higher incident energy, that point right here. All right, so we're looking now at slide number 11. And here on the left-hand side, I'm showing you the TCC that is exactly the same that we showed before. So we haven't done anything yet. I'm just showing now on the right-hand side, if you right-click or double-click on the upstream breaker, the 2500 amp breaker, we're going to look at its settings window and specifically the phase trip window. So in order to implement the maintenance mode, I'm going to go down to where it says RELT. Again, that's GE's specific name for the maintenance mode. I'm going to say turn it on, and then I'm going to select the value. Now, one of the common questions is, how do I know what value to select? Well, there's a couple of ways to do it. You can see if you change the pickup value for the maintenance mode, you get an amperage, and you can select then a number such that you get an amperage that when you compare it to where the arcing current is, also displayed on the TCC, that band for the maintenance mode pickup is clearly below that. So that's one way to estimate it. And the other way to do it is just maybe pick half the value, see what the time current curve looks like, make adjustments as needed from there. So here I'm choosing 6.5 as the maintenance mode pickup, and I'm going to apply that. And then as we advance the slide, you see on the left-hand side is the resulting curves for the 6.5 maintenance pickup. And then for comparison on the right-hand side, I'm showing that the baseline setup without the maintenance mode enabled. Okay, so we'll again hopefully allow you to see this a little more clearly with some of the pen work on the screen. So some of the key things you want to notice here is when I had the didn't have the maintenance mode, again I was clearing in the area I'm highlighting now on the short time part of the curve, and that happened to be 113 milliseconds. Over on the left-hand side, I'm now clearing at the instantaneous speed of the breaker, which is typically going to be 50 milliseconds or less. In this particular case, it happens to be 42 milliseconds. So I've obviously cleared the arcing current faster, and then I get the corresponding decrease going from a 9.4 to a 3.5 calories per centimeter squared. So this is a significant change, and this is the benefit directly associated with choosing a pickup below the arcing current. The other thing to take note of here is what I will call the margin of safety. That is this little distance right here between the left side of the arcing current band and the right side of my maintenance setting pickup. Now in this example, this happens to equate to about 2,500 amps. And one of the things you should be considering in your analysis is, do I have a sufficient margin of safety in this space? 2,500 amps, is that good enough? Well, that's where engineering judgment comes in, and what's the accuracy of my utility data fed into this modeling? What's the accuracy of my cable lengths, which also contribute impedance? What's the accuracy of my transformer data? If the combination of all those variables means in real life, because the real life data is a little different than what you've entered in the software, you could end up with an arcing current that is in fact lower than predicted. And the effect of that would be then, if this rose-colored band were actually further to the left, you might end up with a clearing time that is in fact much larger than what you're bargaining for. Okay? So then should I have more, or if I want more margin of safety than what I'm showing here, what can I do? Well, one option is, and one philosophy is really, hey, this is a temporary setting. It's for protecting personnel, although you would also get a benefit of equipment protection. So since the key variable is protecting personnel, why not just set it at its minimum value? So certainly that becomes an option, and what I will show next. All right, and give me 1 second here. I'm going to erase those drawings. All right, so now instead of having the 6.5x setting, I'm using a 2.5 setting. And now you see a couple of things. One is I have a much larger margin of safety, that distance there. And the other thing you see that isn't a change, but something to take note of, is if I had this, I do have the same incident energy result of 3.5 calories per centimeter squared. I'm going to give you a couple of seconds here to think for yourselves, why did the incident energy not change even though I lowered the pickup associated with clearing that arcing current? And the answer is that I'm already clearing the arcing fault, the arcing current, at the fastest possible speed. Because I lower the pickup further, as long as I'm already clearing at the fastest speed of the breaker, it's not going to get any faster. So my incident energy doesn't change, but I do get that greater margin of safety. The other thing to point out that might be helpful is, as we're going through these different slides, the arcing current never changes, right? The arcing current won't change unless I change particular system variables, and I'm keeping all the system variables fixed here. The only thing that's going to change as we go through different iterations of this is possibly the clearing time of the arcing current, but the arcing current itself is not going to change. So the result here does not change. An example of something to definitely avoid, something I would definitely recommend you do not do, is having the arcing current band straddling two different pickup values. And here's what can happen. So say you're experimenting with your maintenance pickup and you're not showing the arcing current flag or looking in an arc flash report to even see where that number is. Something you could do is just start lowering your maintenance setting pickup value until you get to 7.5x. And what would happen is you're going to see a reduction in incident energy here from 9.4 down to 7.9. And you might say to yourself, if you're not examining this closely, oh, I got a reduction. I guess I'm finished here. But the fact is, no, this is not a good situation to be in, because now see what happens. You've got, and I'm going to bring up the pen here to make sure you're seeing what I'm pointing at. You've got one side of the arcing current band being cleared at the instantaneous speed, excuse me, down here, the instantaneous speed of the breaker. You have the other side of the arcing current band, the 85%, being cleared on the short time band. So the software is going to check both points and see which combination of clearing time and arcing current results in the highest incident energy. And in this case, what's really driving it is this. I know that because EasyPower has told me it's using the 85% arcing current value, because with that larger clearing time, that results in the higher incident energy. So you haven't got all the incident energy reduction you can get, plus you're in a rather precarious situation where your arcing current band is so close to this short time pickup that, again, with any of the possible variances in the real world of the data compared to what you've entered is off, and that arcing current band is farther to the left in reality, then you can get a much larger, higher clearing time than what, based on the data compared to the data you've entered in the software. If I go into the TCC TCC View, where I'm also showing the one line on the left-hand side with an EasyPower, I previously activated the maintenance mode by saying turn it on and apply in the settings window, but I can also, once I have a value entered, I can also turn it off via this view by just going to the breaker that has the maintenance function, right-clicking on it, which will bring up this menu, scrolling down or mousing down to the maintenance mode, and there I can turn it on and off. So here I'm going to turn it on, and then in the next slide you see the curve dynamically changes, so you now see where that is. You still see where the arcing current band is, and you have your arc flash result over in the one line dynamically change. Also, you see there's a symbol around the breaker that has the maintenance mode, and the EasyPower provides the square symbol to indicate I've got this breaker in maintenance mode. Okay, so as a quick summary for the maintenance mode, the key points are fundamentally it's a second instantaneous setting available on the trip unit. It is intended for temporary application because, again, as you lower the maintenance setting, you create more overlap with other devices. When it's enabled, it's going to create that additional overlap, as I mentioned, reducing selective coordination. Key point, it's going to require user intervention to turn it on and off. And, of course, the best arc energy reduction is going to be achieved when that maintenance mode pickup band is below and not at all overlapping the arcing current range. And we also talk about, to the extent possible for selective coordination or the amount of coordination you're willing to give up, provide a margin of safety there as large as possible. Okay, let's transition then into zone selective interlocking. So some basics on ZSI. Basically, it's a scheme between, at its simplest, two breakers, although it could be many breakers to one upstream breaker, where the downstream breaker is going to send a signal to the upstream breaker when the downstream breaker sees a fault. And that basically tells the upstream breaker that, hey, my downstream partner in this scheme sees the same fault I do, therefore I will shift my settings to give the downstream breaker an opportunity to clear the fault before I commit to tripping. This essentially then retains selective coordination while allowing the upstream breaker to be set lower than normally otherwise would be possible without giving up coordination. So this can be done using short-time functions on the trip unit, or it can be done using instantaneous functions, or both simultaneously. But obviously, since the instantaneous response on the breaker is always faster than even the fastest short-time response on the breaker, then I-ZSI would provide the superior arc flash reduction. This is a 24/7 method. That is, it's basically wired at the factory with the trip units that have this capability. And of course, the correct settings need to be put on it to get the right arc flash reduction. But once that's done, it's 24/7 and no user intervention is required, unlike the maintenance switch. So as a quick example, in this little mini one line on the right-hand side, if I have a fault on the bus, fault location A, then the corresponding curves on the top left, the top left graphic of the time current curves, you can see there's substantial overlap that typically would indicate massive non-coordination. But in this case, using both short-time and instantaneous ZSI, this will be coordinated. But if the fault's at A, the main breaker is set low and you get the best response possible from that breaker. If the fault is at location B, what's going to happen is the downstream breaker will send a signal to the upstream breaker, letting it know, I see the same fault, and then the upstream breaker will do a shift or shifts to make sure things are coordinated while the downstream breaker is clearing the fault. So when you look at these lower settings, the protection for the bus, we call those the unrestrained settings. And then when the upstream breaker is moved out of the way to allow the downstream breaker to clear in the case of an active fault, we call that the restrained position. Okay, so some other basics. Similar to what we discussed with the maintenance switch, the ZSI cannot differentiate between a bolted fault and an arcing fault. It only knows current and the amount of time the current has persisted and acts in accordance with the trip unit logic. However, it can differentiate between a fault in or below the zone, and that's the key advantage of ZSI, because it now knows if the fault is below both breakers in the zone or between them. It can then manage its settings dynamically to allow the coordination to continue, even when you have these low settings. So because it's not a temporary measure, it can influence the arc flash label, unlike a maintenance switch. And it is a relatively simple setup, again, if you've done the analysis, in that if I'm, say, using instantaneous ZSI, I'm just using the normal instantaneous pickup value. I just now have the benefit of being able to set it lower. So you can see the graphic on the right. For instantaneous, that's something you're going to have to set whether you have ZSI or not. Similar to the little graphic next to it for short time. I'm going to have to always set a short time pickup and a band, and if I'm using it, a slope. But now if I have short time ZSI, I just get to set my pickup lower and, my delay. Forget the comment about setting the pickup lower. That will come later. I can set my band lower without any loss of coordination. But then for short time ZSI, there will be one extra window where you have to set the restrained setting that it goes to, shown on the bottom right. Again, the key is you must know where the arcing current is and set your devices appropriately, again, with the pickup you're relying to, or the function you're relying to clear the arcing current. That pickup should be clearly below the arcing current. So here now I've clicked on the main breaker again, and we're going to see what settings have to be manipulated in order to have EasyPower model the zone selective interlocking, in this case just for short time. So this is only short time ZSI. So in the panel on the left, we're looking at the phase trip tab for, again, the upstream breaker. The first thing I'm going to be able to do, again, the things in red are kind of changes from the previous times we looked at this window when we're doing maintenance switching. So maintenance switching is off, but the first thing I've got in red is the short time pickup. Because I'm using short time ZSI, I can set my short time pickup lower, creating overlap, but I know ZSI is going to keep that overlap coordinated. The other thing here, and the thing that may need the greatest attention to detail at this point, is the delay. When I'm going to use short time ZSI, this short time delay represents the restrained short time delay setting. That is, this is the delay in the phase trip window for short time that will be used if the fault is below the downstream breaker. I move over a couple of tabs to the ZSI tab. And here, one of the changes I have to make is I do have to check the ZSI box. And then the other thing I have to put in is the delay I want the breaker to use for bus protection. So again, this was the unrestrained setting. Going back to the phase trip setting, something else I just wanted to point out that's kind of in the notes here, but this delay, you want to choose it for, again, on the phase trip tab, the restrained delay, you want to choose it so that it is coordinated with whatever the downstream breaker phase short time delay is. Okay, so we're going to look now. So this is what you have to do on the upstream breaker. Note on the T-ZSI part, let's just ignore that for now because we're going to introduce that a little later so that you can see the effect of adding one thing at a time and not multiple things at a time. All right, so here's now the downstream breaker settings window. And here, I don't have to change anything in the phase trip window. All I'm going to do is address the things I'm highlighting here. So first of all, in the downstream breaker, I do have to check short time ZSI. I also will have a little pull-down window available here that now allows me to select which upstream breaker, because I could, in fact, have multiple upstream breakers that would possibly this breaker could work with in a ZSI scheme. So I'm going to select the main breaker, which the designation is VO1. So I've told the downstream breaker I'm working with the immediate main breaker on this bus. The other thing I have to do, since I've activated short time ZSI, is I do have to force this delay value to be the same delay value that I'm using in the phase trip value, so a 3 in this case. Going through this, it helps to just keep in mind that for a single ZSI zone, that is one where the downstream breaker is not also interlocked with devices further downstream of it in multiple ZSI zones. So we're talking about just a single ZSI zone. In this case, the downstream breaker settings never change. It never shifts, okay? But you do need to put in a value here It says unrestrained setting, and that is correct. It's going to protect whatever's downstream of it, and it should be the same value as the phase trip. And again, for downstream breaker, nothing on it ever shifts, so we're going to leave TSI unchecked for downstream breaker. All right, so with those settings entered, now looking at slide number 23, you see what is possible with the time current curve. So basically what has happened is I've lowered the short time pickup, I've created this overlap, but this overlap is going to be coordinated, and you'll see that in a second when I show you the restrained settings. So in this case, I get a slightly lower value of incident energy, down to 8.1, because I lowered my short time delay band a little bit because I'm no longer concerned about the overlap. The other thing you see is you have very clearly, and I'm going to again try a little bit of pen work here to point this out, very clearly you still have the arcing current range cleared on the short time band clearing time, but I also now have a larger margin of safety than I did in my baseline setup between the short time pickup and the arcing current band. So this is good. Again, the arcing current hasn't changed, but the incident energy went down a little bit. And the 100% arcing current is still driving the result. Okay, so to the next slide, slide 24. Here, I am now going to show what happens if I have a fault below the bus I'm protecting with ZSI. I go to the downstream bus, I would right-click it, say fault the bus, and actually it doesn't matter if it's the immediate downstream bus or any other downstream bus, I would get the same result. And to the right, you see the shifting. So in this case, what shifted was the short time delay band from it was a 3, now it's gone to a 6. And now you get a sense of how the coordination is maintained, even though we started with that overlap. So again, this is the position, this is the restrained position you get only when you have a fault downstream of the downstream breaker in the scheme. Note that where the instantaneous parts of the curve begin to overlap, to the right, from that area to the right, it is still uncoordinated. All right, so at this point, let's add in T-ZSI, which I haven't even defined yet. T-ZSI stands for threshold ZSI, and threshold ZSI is to pickups as ZSI, without any other qualifier, is to delays. So whereas short time ZSI kind of managed the delays to keep things coordinated, T-ZSI is going to manage movement of a pickup to keep things coordinated. So what threshold ZSI allows me to do is lower the pickup of the upstream breaker to the point where I can overlap the downstream breaker. So the first thing I've changed in this window, highlighted in red, is going to be I went from a pickup of 3 to a pickup of 2. This is going to create overlap, but as you will see, it is going to be coordinated. The delay of 6 in the phase trip window and the delay of 3 on the ZSI window, those are unchanged. We don't need to change those. Those are set appropriately, and I still have short time ZSI selected. But then the other change I have to do, just coming onto your screen now, is I do have to select the T-ZSI. However, this is one of those situations to do all this right. You got to know the software. You actually have to know the trip unit, and then of course analyzing the resulting time current curves is very important. But here's a detail. You know, in the notes for this breaker, it would say, you know, here's the designations for the various time current curves, and a title for or nomenclature for the breaker's application guide. The only way you'd know this information I'm telling you now is by checking those resources. Is T-ZSI would not be available unless you have a certain firmware of this trip unit, and you also have the same trip unit optioned with the I-ZSI. So realize this is one of the things you have to be careful about. You only want to select T-ZSI if you're sure you're working with a trip unit that actually has that capability and the right firmware version. Okay, so here now is the time current curve with the T-ZSI included in the capabilities, and you see again the overlap of the short time pickup, the short time band, and then we still have overlap in the instantaneous area, but we're not using I-ZSI yet, so where that begins to overlap in the instantaneous area from that point to the right is still uncoordinated, but now everything to the left of that dashed line is coordinated, even though it doesn't look like it. And we're going to show you the restrained position in a moment. But again, now the benefit is, even though I had a good safety of margin here before, now it's even increased, and certainly in situations where they're already very close together, being able to move my pickup of my upstream breaker further to the left, like I've done in this case, can make a real difference in getting a nice margin of safety. In this case, we already had a decent one just using short-time ZSI, but in other cases, it can really be the lifesaver of moving that a safe distance away from the arcing current. So we've got that, and of course the incident energy hasn't changed because we're still clearing at the same time both sides of the arcing current values. So the next slide here is oops, I missed one. There we go. The next slide here is showing what happens when I fault a bus below the downstream breaker, and now you're seeing in the time current curve two shifts. You're seeing the short time pickup of the upstream breaker has moved to the right, and you're seeing the delay band of the upstream breaker move from that delay 3 to the delay 6. And again, visually you can now look at it and see the white space between the two breakers. Again, this is the action of the ZSI, and this is what maintains the coordination in this example up to the point where the instantaneous parts of the curve overlap. All right, so a quick short time and T-ZSI summary. So for short time ZSI, it allows the breaker to be set with lower short time delays without reducing selective coordination. What the short time ZSI does, it shifts the upstream short time delay for faults below the zone. It's a 24/7 setting, no user intervention required, and where the curves overlap in the instantaneous region, it's still uncoordinated. In the T-ZSI, summarizing that, it allows the breaker to have lower pickups without reducing selective coordination. The lower pickups are coordinated even though they overlap the downstream breaker's short time pickup. The T-ZSI part actually shifts the pickup, and it does that automatically. It's not something you select. It shifts it by 23%, which always ensures white space between the two breakers. And T-ZSI can be used with short time or I-ZSI. So I just showed you an example with short time and I-ZSI, excuse me, with short time and T-ZSI, and the very last thing I'm going to show you is combining all three. I did see a question come up about what are the units for delay 3 and delay 6. In these particular trip units, there are no units associated with it. You would have to look in the breaker documentation and see what the associated clearing time is. You can certainly go to the time current curve in the time current curves in EasyPower, and you can see if I use the 3, go to the top of that band, and you can see what the clearing time is. All right, so now the final thing we're going to look at is combining all three: instantaneous, short time, and threshold zone selective interlocking. My delays for short time aren't going to change, still using 6 and 3 on the left and right hand windows. But the thing I do have to change now is I also have to check, as seen there in red, the instantaneous ZSI block. So I got to make sure they're both checked. And I am going to check the T-ZSI. It was already checked, so we're really not changing that. But again, you should only do that if you've got the right firmware. And the other thing that I can change now is, you see back over on the left-hand side, I'm going to be able to change this pickup on the instantaneous setting to something much lower. It was 30,000. I'm now going to be able to set it to 12,500 because the overlap will not give me a coordination penalty. It will be coordinated. All right, so here's what the time current curve looks like with using I, short time, and T-ZSI. You can see the pickups for short time and instantaneous overlap, as well as the bands for short time and the timing and the instantaneous foot. They're all overlapped, but again, because of the action of ZSI, these are all coordinated now. So in addition to the coordination benefit I get, of course, the thing we were most focused on is the arc flash result. Now I'm clearing the entire arcing current band at the fastest time of this breaker, and in this case it's 50 milliseconds, And you can see that the result is 4.2 calories per centimeter squared. So again, that's a noticeable reduction from when I was using short time only. What happens if the fault is below the downstream breaker? This is what happens. I'll fault the downstream bus, and here you see that I have a white space due to the shifting everywhere between the two breakers. The short time and instantaneous pickups shifted to the right. The instantaneous timing shifted upwards, and the short time band shifted from, again, the 3 to the 6. Okay, and before I go to the next slide, I'm going to jump out of the slides here for just a quick moment, and hopefully you're able to see now the actual EasyPower screen. And what I just wanted to show was this dynamic changing of the time-current curves kind of in real time here. So now this is what the main bus faulted, 4.2 calories per centimeter squared. And I'm going to show you what happens when I fault the downstream bus. You see then that the upstream breaker does the shift I just showed you statically. So again, the software is doing this, and I can keep going back and forth doing this. Hopefully the webinar is keeping up with it. I can keep doing this, and again, the movement of the time current curves is exactly what the trip unit would do. Okay, so back into the presentation, and we're going to do a summary here. Now first, just starting for the I-ZSI part, which we introduced last. I-ZSI allows for selective coordination up to the available fault current available. And this is when both breakers have instantaneous protection and overlap on the time current curve. Now, there are some limits on this. So in some cases, the limit of coordination might be up to 85K, it might be up to 100K. It just depends on the particular set of breakers you're using it. But certainly for the example we just showed, I can now get coordination up to the available fault current when I could not do that before without using I-ZSI. 24, again, it's a 24/7 measure and no user intervention required. It's going to give you a faster arc clearing time compared to short time, naturally, since the instantaneous function is faster. And then transitioning over to a overall summary, tying this back to the code article we first introduced. The 2014 edition of the NEC does require the arc energy reduction method to be used on 1200 amps or greater. Again, there were 5 listed in the 2014 version of the code. Some of you know there's 7 listed in the 2017 version of the code. But it all applies to breakers 1200 amps or greater, and we focus on 2 of the methods, maintenance switching and zone selective interlocking. Reducing arc energy requires a fast clearing time at the arcing fault amperages, which hopefully you saw are less than the bolted fault amperages. So just think of, we use the 50 kA available source. Our bolted fault amperages were at, our arcing fault amperages were down at 24 kA or less, so less than 50%, and that's typical of a 480 volt system. You're going to be 50% or less the arcing current compared to the bolted fault current. Maintenance switching is a temporary measure, and that requires user intervention to enable the arc energy reduction. ZSI is a 24/7 measure, does not require user intervention for the arc energy reduction. And the last point I want to leave you with, and hopefully something that I've made the point sufficiently prior to this, is that having a maintenance mode and ZSI available on trip unit in itself is not going to give you the arc flash energy reduction. You'd be lucky to get it unless you specifically are setting the devices correctly in relationship to the arcing current. Okay, so that concludes what I wanted to show for the webinar. I've got the last slide shown with my email. If you want to email me, and anybody else, feel free to do that. Be happy to answer additional questions. I thank everybody for their attention today and joining the webinar, and I thank EasyPower for the opportunity to provide this information. Thank you very much and have a great day.